So it is now being recorded. This meeting. Generally, we should not have a problem, I believe.
No, it's fine.
It's fine. It's not a problem.
Ratan, as we know, will be anchoring this. I'll just bring on the slides in keeping it in readiness for the start of the meeting.
Yeah, good evening, Vijay Kumar.
Prashant, how are you?
Fine, fine.
It looks there may be a problem with the link. Maybe many people didn't get the link properly.
Is it?
I think so many people are joined so late. I don't think that should be an issue.
No.
As a matter of fact, I also received the link directly from Vijay Kumar. Otherwise, it was not there on the SNT group.
No, it was.
So
It was posted in the Telegram, not on the WhatsApp.
Okay. Because I was searching in the WhatsApp.
No, it was posted on the original link was posted on Telegram.
Okay.
Ratan, will you take over now and we can start the meeting? And what we should do is you will run the slides yourself, Ratan? Ratan, will you be able to run the slides?
You are
yourself?
on mute, sir.
Sorry. Yeah. Don't worry. I'll open the slides when I want. Leave the main slide now. Okay.
Yeah. So
Okay.
I have removed the slides, so you can go and take over and get the meeting going.
Okay. I'm starting then. So I warmly welcome all participants to this third session of the Forum for Radio-Based Signaling. Good afternoon to you all and good evening to the friends in Australia. When I joined in Indian Railways, I think in 1979, I'm 17th batch. So every railway had quite a few signaling veterans, whom we fondly or respectfully called signaling experts. They knew thoroughly, I think, every aspects of signaling technology available that time. I mean, mostly electromechanical, mechanical, and few RRIs. And they are all our gurus. Now, in between, some revolution happened, and with the adoption of electronic processors for realizing safety functions, along with this digital networking through modern radio technologies, all this networking, these have made the whole signaling very, very complex and highly process driven. You see any signaling document, so one can find a very long list of standards. There will be a lot of EN standards, IEC standards, IEEE standards, then, UNISIC subsets, a hoard of documents, then TSI, technical specification for interoperability, then CSMRI, and there is a field determination, and there's a host of new activities which is unknown when I joined railways. These are all new things, and everything actually came after the introduction of software in safety. Mostly, I mean, grossly we can say that. And so a lot of new activities also, like RAMs, validation, seal determination, safety assessment. I mean, there are many activities that has come into the signaling profession. And another thing, all these things, they are not done in one layer. If you see from the product development, where the product is being developed, they do very meticulously from the on a module level, subsystem level, and then the product is made after a lot of processes, so that the systematic failures are minimized and came to a seal4 level or whatever level is determined, and then the product is given to the field. In the field, again, then they are subjected to a lot of hazard analysis, risk analysis, then QRA quantified risk assessment, and there's a whole lot of activities, So it is now very, very complex. So after working in railways for about 40 years, so I can at best claim myself as a senior student of railway signaling and control system. Today, only a team of experts knowing different facets, different issues of the system can successfully build a safe and reliable signaling system. So that's a specialty. So what I told in the beginning, when I joined railways, the railway gurus, they had everything in control. They knew how the notch has to be cut in the mechanical lever frame. They knew how all the relays and things are working. They knew all the control tables. They know all the test forms. But now it's very difficult. Now you really need specialists from different fields to do something in railways. So today the key is collaboration. Here lies the importance of this forum, where the rich experience of distinguished railway professionals is shared. I'd like to thank my friend Somnath Banerjee, who is an eminent SNT professional, for creating this important forum. And he's doing a great service to railway community. Today, we have two very distinguished signaling professionals with us, Mr. Vijay Kumar. I knew him from Mughal Sarai days, very brilliant. He's now in Australia. And my batchmate, again, wonderful person and very intelligent, Gurmeet Singh Tuteja from India. Mr. Vijay Kumar will cover CBTC, ETCS, and PTC, whereas Mr. GS Tuteja will cover the aspect of integration of CBTC with rolling stock. Let me introduce you the distinguished speakers in a little bit detail. I'm taking over. I'll open their CVs and I'll show you. Can you see my laptop? Of course, you won't see. Can you see Mr. Vijay Kumar's CV?
No, we can't see that. Sir.
You can't see?
No.
No,
we cannot. We are seeing you, not the.
Okay, good. I do again. I'm trying to take over. I come again. Okay, now?
Yes, now it is okay.
Okay, good. Okay. So I put in a monitor, so I have to turn a little bit of the camera. So Mr. Vijay Kumar, he's Associate Director Engineering of Rail Systems, Sydney Metro, TFN ASW. Vijay Kumar is a Fellow of Engineers Australia, Fellow of IRSC, AMI Ming Course, APEC Engineer, and INTPE Australia, RPEQ, with over 32 years of railway signaling experience. Vijay Kumar is a Chartered Engineer UK, Chartered Professional Engineer Australia, and holds NER registration with Engineers Australia. He has the areas of practice in CP engineering and NER for electrical engineering, information technology, electronic engineering, system engineering, and leadership management. Vijay's specialism is communication-based signaling system CBTC and ETCS. He has been directly involved in novel projects of Metro in Delhi Metro, Sydney Metro, and ETCS Level 2 as Technical Director of Auto Hall Projects and Raw Hill Project. Vijay has a proven track record in leading integrated railway train control and signaling system for major projects like Fast 3 lines in Delhi Metro, world's first driverless heavy haul train based on ETCS level 2 and ATO, Ray Haul project with ETCS level 2 and with virtual bellies based on GPS, ETCS level 2 with Horizon, ETCS projects in Adelaide and Auckland, Sydney Metro driverless CBTC, and his experience ranges from broad range of signaling systems from metro signaling, CBTC to ETCS. He started his career as a IRSCC, like all of us, with Eastern Railway as STDST, as Deputy CST DAMRC from 1998, and subsequently from 2003 as Chief Signal Engineer in DMRC, Vice President Freight and Engineering in Ansaldo STS, now Hitachi Rail STS, Head of Engineering in Siemens Mobility Australia, New Zealand and ASEAN. Vijay has considerable experience of engineering management, system engineering, and safety management, presenting a number of prestigious conferences on train control and signaling system. So, thank you, Vijay. Now I want to introduce our friend Tuteja, Gurmeet Singh Tuteja. GS Tuteja, Chief Signaling Expert. He's presently working as Chief Signaling Expert in Louis Berger, India, and working with general consultants for Mumbai Metro Line 3 since February 2018. Worked as officer on special duty SNT with MMRDA for metro projects from January 2017 to February 2018. Retired from Indian Railways after 37 years of service as CSTE in November 2016. Okay. Moment. I think there's another page. Okay. He's an electronics graduate with postgraduate qualification in industrial engineering, specializing in operations planning and control, project management, management information systems, having experience of 37 years in Indian Railways, in S&T, performing multidisciplinary role covering operations and maintenance of signaling systems, safety management, project management, personnel management, budgeting, and cost control. Very wide experience. So now I don't want to take any more time, valuable time. I would request Mr. Vijay Kumar to start his paper. Once he finishes, we'll take question and answer session. Then Mr. Tuteja will start his session. Thank you.
Can you see my screen?
Yes, we can see.
It's visible.
Okay, so thank you, everybody, and thank you to Mr. Mukhopadhyay, Mr. Banerjee, who were my mentors in Eastern Railway when I was a young kid. So it's long time back in 1990 to 1998, we were there. So Mr. Banerjee asked me to present on freight CBTC, ETCS, PTC. So I will. It's a very long topic, so I have prepared a few things to say, talk about PTC, to talk about CBTC. I won't go into explaining what is a CBTC, but generally when we talk about what standards and grade of automation and functions we should look at, what's the current state of play in ETCS, and talk a little bit, which is more interesting to see what's happening in the world of fixed block, moving block, virtual coupling, etc. New thing on the product horizon is track-centric to train-centric CBTC, ETCS level 3 and way ahead, and finally a few important points about level 2 implementations in Australia for auto haul and rail. So I start with PTC. I won't spend too much time on this, but just to give you, PTC was actually enacted by the US government as a safety improvement mandate. That was in 2008, and they wanted everything to be completed by 2015. It's a federal law. It's still not happened. It's still ongoing. So all lines which were supposed to have more than 5 million tons of traffic per year, any line which was carrying toxic, inhaled hazardous material, or any line carrying commuter or intercity. But then people will say, what is PTC? ETCS is very widely known. CBTC is very widely known. PTC is something that everybody keeps talking, but has a different definition for different people. So PTC is basically an integrated communication-based train control and track management system, which authorizes trains, equipment, and people to occupy track, moving safely and efficiently in dark territory. So this is the definition of PTC, is any system that prevents train-to-train collisions, overspeed derailment, incursions into work zones, derailment due to switches in wrong position. This is the formal definition of PTC, which is basically performing the function of safe train separation, dynamic speed profile, including PSR, permanent speed restriction, maintenance blocks, track blocks, switch control and monitoring. That's what PTC is the normal definition. And there can be systems which vary in complexity and sophistication depending on the level of automation and function and degree of control. So the main PTC implementation is a Northeast Corridor, which is the access plus cap signal adopted by Amtrak and other passenger line. It has been developed mainly by Alstom. Then there is a Class 1 railroads, which is the freight lines all over the US, which is ETMS, now VETMS, developed mainly by Wabtec. Others are also getting into the picture. And ITCS, which is GE, but now Alstom, which is the one developed by. So this is the Northeast Corridor. So you can see there are wayside signals with track circuits, coded track circuits and cap signal for train separation, balises for PSR and positive train stop at interlocking, radio for PTS release and TSR delivery, and there is a centralized server. So it is nothing but ETCS level 1 plus a radio infill and a TSR server. Whatever name we may give, whether it is a PTS, positive train stop, or releasing with a cap signal with the coded track circuit, but it is basically an ETCS level 1 with radio infill. It works on a 220 megahertz radio system. And this is the more, let's say, more famous for the Class 1 generic PTC system, which you can see is basically an ETCS level 3. But without balises, but based on GPS. So again, we can see that there is a central office, which is what we call TMS, an onboard, and a DMI, which is very different to what we see in Europe, and an onboard, and there are interlockings, and also manages dark territories. So you have an office, which is the VPTC server, an ATP on the train, a GPS-based location determination unit, and basically a server for central distribution of timetable and mission, etc. So it is no different than ETCS level 3, but without balises. And the functional allocation is slightly different. So there are many implementations. One is exactly similar to ETCS level 3 in terms of function, but others can have the interlockings also talking to the onboard. So there are implementations where the central server is only doing the non-vital, and the interlocking is communicating with the onboard in order to either extend the movement authority or stop it. So that's another implementation. So two different implementation, but they're all called PTC. So I'll not spend too much time on PTC because I don't think it's of too much of interest. It's only in the US that it talks about. So let me talk about CBTC. So again, the most important thing when we are specifying CBTC to procure it for any new line or even an overlay is to ensure that we put together, we specify these three standards, 62290-1-2-3. I think this is the fundamental. Otherwise, people think it is IEEE 1474. 1474 is good to define the CBTC definition and some function, but 62290 is where we talk about the grid of automation. So talking about the system principles and fundamental concepts, functional requirement in part 2, and system requirements in part 3. And basically, we must ensure that coupled with this, we also specify 62267, which is the safety requirements. So as Mr. Mukhopadhyay earlier said, that nothing comes in isolation these days, it comes in a package. So if we specify only the functional requirement and not the safety requirements, then there will be an issue. So we need to specify this IC 62267. And also, we should also include the part 2, which has come out in 2011, which is the hazard analysis at the top system level. And we must also remember that all these standards, they give you options of mandatory and optional function, depending on what we want It's the operator which needs to select as to what the operator wants. Just merely mentioning the standard is not going to solve the problem. And obviously, as I said, 1474 must be kind of specified, because these are used by all suppliers. At least I know of 3 that I have worked with. Everybody gives a mapping to IEEE 1474. So whatever we need in terms of functional requirement or user requirements, interface requirements, or what do you call these allocation of functions, and the testing practices for functional testing of the system. We as a matter of practice should define and specify these standards. It helps in getting what we want. But the real important thing is that we need to look at the relationship between these standards. So specifying one and not specifying others can lead to some gaps. So as I spoke in the beginning, that we have the system requirements, 1474.1 to user requirements to functional design and up to test and commissioning. So that is why it is important to cover the whole V cycle to specify all these standards. So this is a very generic CBTC. As I said, that I will not go into the details, but just to give an idea that this is a generic CBTC solution where we can have main equipments, which are the central equipment of central interlocking, can be distributed as well. It is not necessary to have centralized interlocking. Zone controllers, maintenance servers, automatic train supervision. Then we have in the control room centralized equipment for TMS, plus other facilities like SCADA, power, etc. That is true for all metros, even 20 years back, and a backup. The important thing is that we define all what is needed in the train, as well as on the wayside, the platform screen doors, and the security systems, passenger information system. So as I said, I will not go into explaining what is a CBTC, but just wanted to use this as a reference for the next topic. So coming back to the point that I was making is that there are some core CBTC functions and there are some non-core CBTC functions. And what I mean by this is the core CBTC function, they have ATP, automatic train protection, automatic train operation, and automatic train supervision. Basically, what it means is positioning, train tracking, propulsion and braking control, routing, movement authority, interlocking, regulation, scheduling, and communication. This is given. Whichever supplier will come, the core functions will be given, whether you specify or you don't specify. But the trick is when we start looking at the non-core functions. This is where we start looking at how do we meet the operator's unique operational needs. Otherwise, inadequate functions will kind of make the system not delivering what we wanted. Some examples are, these are just some examples. Train recovery. So I was watching the recording of last time. People talk about backup signaling, overlaps, etc. It's absolutely not needed. I think if you are doing CBTC, we should not even talk about overlaps. And we should not even talk about backup signaling. There are basically 3 methods that people or all companies deploy. One is that you can create a safe zone by what is called a block area of line and let the non-communicating train move so that it can go back to the depot. Second is that we can send what we call a recovery train to couple it and bring it back. And third is to provide the backup signaling. But it depends on what we want. I think it is unnecessary to ask for backup signaling. Then the work zone protection. Again, this is one topic which is slightly missed. We think emergency stop plunger or some staff protection key switch is enough. While it is distributed and may serve some purpose, and what is implemented in ATS is not SIL 4. It's not vital. It is at the best SIL 2 based on procedures that are supplemented with it. So there are solutions these days with work zone protection that needs to be looked at. Then obviously work trains, everybody's equipping now. Diagnostics is very important. Fallback mode. We spoke about the fallback mode in any case. How do we launch trains? That depends on which grade of automation we are talking about. We are talking about grade of automation 4 or grade of automation 2 or 3. So depending on 2, 3, and 4 grade of automation, this function becomes very, very important. And then last is the migration strategy. So coming back to this grade of automation that I was talking about. So as we all know that it is defined not in IEEE 1474. It is defined in 62290 IEC-1. So these are the 5 layers. GOA 0 is manual operation. Driver controls the train manually. There may be signals, may not be signals along the track. So if you look at the 4 core functions that are taken to define them is setting train in motion, stopping the train, door closure, operation event of disruption. Goa 0, everything is driver. So when we talk of Goa 1, which is SCO, supervision and control train operation, here we may have cap signal or can have even line side signals. Here again, we can see it is all driver. The moment we go to Goa 2, which is ATO, but there is a driver. So again, we can see that the door closer is driver. An operation, the emergency operation is driver. Rest is automatic. Goa 3, there is no train driver necessary. The train is driven and controlled fully automatically. Attendant is for emergency situation. Here, the only difference that we can see from Goa 2 is that the door closer can be automatic, can be attendant, but the emergency is still with the attendant. When we go to Goa 4, that's where it is all automatic. And depending on which grade of automation we are defining, here you can see between the different Goas, these are these, let's say, the core vital train functions for train operations. So ensure safe movement of trains, drive the train, supervise guideway, supervise passenger transfer, operate a train, ensure detection and management of emergency situation. So when we look at Goa 4, everything is by the system, except the last one where there is some involvement of the OCC. Even in Goa 3, you can look the number of crosses. So the number of crosses are, that means there is quite a manual thing that a backup is there. Goa 2, again, we can see less and less. So when we are specifying a Goa 2 or a Goa 4 or Goa 3, we need to look into this table, see what we want, and then define accordingly in the specifications. And I will not go into each of them, but again, depending on the grade of automation, the train supervision and operation function, the daily timetable. Timetable can be very simple for a Goa 2, and it can be very complex for a Goa 4, when you want the trains to wake up on the stabling line and be launched automatically. So those functions then need to be defined accordingly for a Goa 4 and a Goa 3. So then I will come to ETCS. I'll speak about track-centric and train-centric CBTC a little bit later. ETCS, the current state of play. This is level 1. As I said, I'm not going to go into explaining what is a level 1. Everybody today knows what's a level 1. So we can see that what the TMS, the interlocking and the LEU, and how the train is moving with its speed and distance. So you can see the Euro loop or the LEU and the balises. When we go to level 2, we start talking of an RBC, and then we start talking of a train separation, which will be less than, and we may or may not have signals in level 2. Level 2 can have signals. If it is overlaid, it may not have any signal at all. Then I think this is the level 3, which is where we don't have any, we may or may not have train detection. But I think what is to be looked here is the minimum train separation that is getting reduced based on the principles of working that we have and the safety margin that we have from the danger point to the second train to the first, and addition of one particular thing, which is called train integrity monitoring, which comes into play. And the next one that I would like to talk about a little later is, but to talk about ETCS level 3 hybrid, which is another one of the subsections of level 3, which is where we have virtual blocks as well, apart from the what do you call this train detection system as well, track detection system as well. So we can have virtual blocks, and these virtual blocks can let trains come closer than what it can do in the normal level 2. Two other points that there is an ATO over ETCS that has been defined. I think the Rio Tinto one, that auto haul, is a ATO over ETCS, but non-standard, because at that time these subsets were not there. Even Thameslink, which has been done by Siemens when I was there, that's also not standard as per this. The first one that has happened has been recently done by Siemens, I think in Hamburg, where they have put Hanover, I think, Hanover or Hamburg, where they put the first ATO over ETCS as per these subsets. So there is a definition of all these subsets on top of ETCS, which is the subset 125, 126, or the ATO trackside to ATO onboard. Between the train and the ATO onboard is subset 130. ATO onboard to the train is subset 139. There is subset 129, and all these have been defined. They are still in the process of the way the European community works, but these are well defined as being used by PIN. The next one is this is the important one. I think one of the fundamental difference when we talk about ETCS and CBTC is that ETCS, whether level 2 or level 3, is only ATP. Not even interlocking, not even ATO, not even ATS. Whereas CBTC is talking about ATS, ATU, and ATP, all of them together. Whereas ETCS is only talking about ATP. And the only thing that is interoperable is the air gap between the wayside and the onboard, whether it is the RBC to the onboard EVC or between the bullies to the onboard. There is no standard interface between interlocking and RBC. There is no standard interface between TMS to interlocking or RBC to interlocking, or even interlocking to interlocking. The only thing that is standard is the RBC to RBC. Rest, every supplier wants their own. So there was a European project NGTC which was looking into all this. But I don't expect, to be honest, these things to materialize in a way that suppliers will give up their proprietary markets. Then the next important thing is the systems are working. So nothing to explain here, but I wanted to use this diagram to say where the industry is moving. So this is traditional level 2 or even a CBTC earlier days, or a distance to go ATP, which was working with a fixed block with track circuits. So as we can see that depending on the position of the train and the status of the track circuit, the movement authority is extended. But that is fixed block, nothing to really talk about. Moving block, as we can see, we go on the concept of an absolute braking distance. So we have what is called a brick wall concept. So the brick wall is behind the first frame, which includes the margin in order to take into account the uncertainty of the odometry, the rollback distance, plus other errors which could be there. Based on that, the movement authority of the second train is just before that brick wall. That's between train T1 and T2. And then as the train moves, this is what we start getting into, that it moves along with the trains. So the moving block, that's why it is called moving block. But I would come to what is happening in terms of the efficiency / inefficiency of moving block. Currently, when people talk about in the metro world for a CBTC with a moving block, in the nominal mode of working, it doesn't matter, because with the interstation distance of 1 kilometer or 1.5 kilometers, the nominal separation vector is almost more than 1 kilometer between two trains running at a 2-minute headway or a 120-second or 90-second headway. The issue comes when there is a disruption. The issue comes in the recovery and the regulation back into the timetable. And that's when the moving block or even a fixed virtual block would have helped. So in the nominal mode, it doesn't matter fixed block or moving block. And that's why metros go for moving block, because the interstation distances are small and the recoverability is a challenge. And that is why moving block is important. But and this is one of the important points, is to look at that when we have a fixed block, you can see that because of the track circuit occupancy not being there, there is a disturbance, a perturbation. So the train keeps on moving like this with a disturbance till the time the previous train has moved and then extends the movement authority. Whereas if you look at moving block, it keeps on moving as the train keeps on moving. So the separation that is happening between the train distance, there is an improvement. But that is theoretical. But the important point that we have to look at is the inefficiency in moving block. So as we talked earlier, that the movement authority is based on the absolute brick wall concept. And then the reality is this: even if the trains are moving, the movement authority of the train behind is not extended unless we get a position report from T1. That means for a certain duration of time, the movement authority remains what it is. And then it is extended once the position report is there. And that is causing inefficiency in the system. So reduction of headways is an issue. So there are solutions which have come for that. But let me talk of this is a concept which is at the European level right now. So this is mainly applied for mainline, but can also be partially applied for metros. So here we talk of virtual coupling, system based on train-to-train communication. So if we have two trains with, let's say, 100 kilometers per hour, and then we have this movement authority that is given. So what happens in this case is that we open the braking curve of the train behind to the same speed of the preceding train. So that means it is not targeting at this point. It is not targeting at the brick, but it is assuming that this train is moving. So and it creates a coupling area. And then this coupling area is activated. So the following train then approaches, maybe even at a little bit higher speed, and approaches the coupling area. And then what happens is, then they couple together because they are talking to each other and they are locked. So this concept is right now, let's say at the concept level, people are working on it with a lot of emphasis on the system definition and the safety analysis. And this will be mainly applicable to freight, which will be a great improvement because you can have a platoon of trains, a carousel of trains going and can have efficiency. So rather than going to level 3, you can have a virtual coupling, which is much more efficient because you have a train-to-train communication. In fact, we can have an ETCS level 2 with an ATO with optimized block, which can give as good a result as ETCS level 3. So then I come to the track-centric to train-centric CBTC, because this principle is also applied to CBTC or metro. Traditionally, the way mass transit systems have evolved is that we put an interlocking and the ATS, and then we put ATC, which is the ATP and ATO, as an additional layer on top of interlocking. And then the train-to-train communication is always through the wayside controllers. It also takes time. So if you look at this, so the ATS sends the mission. What do I want? Then it sends the route request to interlocking, goes to object controller, then to a point and route is set, comes back to the zone controller, and then movement authority is given. So there is a lot of, let's say, a lag. There's a lot of time delay that happens. And that is why this is what happens in the normal track-centric system. In the track-centric system, this is the inefficiency that we have, as we saw in the moving block as well. And this timing does not help. So what are the solutions now? So what we need is a consistent information path. We don't need to synchronize interlocking and ATC. This becomes one unit. So what happens now is that it is the train which is asking for the, let's say, the resource of the track. So the train requests the object controller. More or less, you can say it is kind of an interlocking, but not an interlocking. It says, I want these track sections. And the object controller will drive the point and kind of reserve the section and give it back to the train. And that is how we are able to reduce the latency and all the time response within the system. People are talking about at least having a 20% headway reduction. So this is how it works. So you can see the previous train here, and the train following is here. So basically, the second train behind asks for a location request. And then this train ahead will give a location report and commitment. Based on that, you can move the movement authority right up to the rear end of the confirmed rear end of the train. And this makes it much more efficient and having a reduced headway. And currently, the only system that I know of is from Alstom. I don't know of Siemens and Hitachi or other companies, but or Thales. Urbalis Fluence is their product name. This is now in progress in France in one of the lines. And recently, a couple of months back, I saw that line 18 of Grand Prix Express has been awarded with Urbalis Fluence. This is the solution, basically. Their architecture would be slightly different, but the concept and the principles would be the same. Then we talk of level 3. So there are very different views about what level 3 actually is. Some people say it means moving block, but level 3 can be moving block or virtual block. It means no track vacancy detection. Level 3 track vacancy detection is optional. So all kind means trackside uses reported train integrity information. This is what is a general concept that everybody, because level 3 is not really defined in a great detail. So if you look at ETCS spec, subset 23 does define that a level of ETCS that uses radio to pass movement authorities to the train. Train level 3 uses train reported position and integrity to determine it is safe to issue the movement authority. Subset 26 also talks of this about train position and train integrity supervision by the trackside RBC in cooperation with the train. Then functional requirement specification also it talks about that. So whilst the ETCS even baseline 2 or baseline 3 does define, but there are details which were not consolidated. So in reality, level 3 does not mean it can be moving block or a virtual block. Need not have a track vacancy. Can have, may not have. It's optional. And then you need to have a track integrity, train integrity information. So that is the reality of what a level 3 is. And based on this, so if you look at this level 3, it's an evolution of ETCS level 2, where the track-based train detection would no longer be required. That's a kind of a goal. But recently, ERA and Shift to Rail have analyzed and defined 4 different system types. Moving block with TVD, which is track vacancy detection, moving block with TVD, virtual block without TVD, and virtual block with TVD. There are some animations as to how it works, but I can maybe in interest of time may not be suitable, but if time permits, I can show it later on. So basically, when you look at level 3 hybrid, so we have level 2, as you can see, these sections on top. And this is the conventional signaling section. And then you have level 2 sections with the marker boards, which are defining in the signals. In the hybrid, we define virtual subsections within the sections itself. So conventional trains can operate based on color light signal on conventional signaling section. Level 2 trains would operate based on the marker board positions, and therefore only one train in each ETCS section, which is this section, whereas hybrid can operate on virtual blocks, virtual red sections. That means we can have more trains entering into a conventional signaling section and a level 2 section. But what we need to understand that even if you want to run hybrid level 3, we still need to fit it with train integrity, the hybrid level 3 trains, because hybrid level 3 trains, if you are using virtual blocks, virtual sections, we cannot run it on a trackside detection. And that is why it is complex and not complex. So the challenges are still there, proving train integrity, because we are talking here not only of passenger trains or a fixed train concept, we are talking of freight as well, and a mixed traffic. Non-communicating train, failed or non-fitted. How do we use trackside-based train detection if no ETCS train information is available? Mixed traffic operation. Legacies of the real work. There are existing trackside infrastructure migration. Need to migrate the entire fleet before you can go into that. And then need to have the train integrity monitoring solution available and fitted on all type of trains. So what's the status of level 3? So it is going on. There was a change request 914 ETCS, which looked at the assessment of some operational scenarios. As you can see, this is a UNISIG document, which dealt into some of the level 3 issues. Then there are specifications in European project shift to rail. So as you can see, there are now we have for a moving block or a level 3, a system definition, operational rules, engineering rules, and safety analysis has been done. Then there is for the ERA, the user group, not the ERA, the ERTMS user group. They also created a specification for a hybrid ETCS level 3. And this was done in 2017. There have been some implementation / demonstration that has happened in network rail. And in fact, in network rail as well as in Amsterdam, Holland. So those have happened in 17 and 18. Right now, with this shift to rail specifications having matured to a larger degree, there are demonstrations ongoing for level 3 as well. But as I said, that there is a difference between a level 2 and a level 3. So if you look at level 2 and a level 3, you can see the RBC will change. Maybe the interlocking and RBC will become one unit. So there are changes which has not happened. And similarly, for onboard, one has to add the train integrity monitoring. It is not currently part of TSI, expected sometimes in 2022, hopefully. Then maybe in the next 10 minutes, I can talk a little bit about AutoHaul. Mr. Tuteza was a little bit more interested in this, so I can explain this. So what is AutoHaul? This is the highlight of my career, by the way. I never failed to mention this. This is the biggest and the most complex project I've ever done in my life. AutoHaul. So basically, what is this? So Rio Tinto has a line around 9 mines over here and goes up to the port. So they carry iron ore and take it to the port, and then it is shipped. So it is around 14 to 1700 kilometers of track. And at that time, when I left the Ansaldo at that time, when the project was finished, was around 180 locomotives. So what basically it meant is that we wanted the train to start from the mine unmanned. So and then move driverless, and then it was going up the hill. So there was a banker locomotive attached as well. So the banker had to come in the area called Rosella, which is where it was at grade, and the bankers would automatically separate while the rest of the train will continue to move unmanned onto the depot, unloading, and then come back. The banker, which was detached automatically, would then do a change of end automatically and go back to the mines for the next service. That's what AutoHaul is all about. So if you look from a concept point of view, it's mine to port, port to mine. Trains were 2.5 kilometers long, 234 wagons. more than 32,000 tons of iron ore when loaded. So in the empty train, if there was an emergency brake application, there have been cases that trains have derailed off the track. So non-application emergency brakes, lots of complexity for an empty train. So basically, it's the world's first autonomous heavy haul train. It's in the Guinness Book of World Record 2020. Okay, and it is the first ETCS level 2 system in Southern Hemisphere. So basically, as I said, Rio Tinto had an existing system which was done by Ansaldo based on the Swedish ATP system, but with no line side signals. It was also based on cap codes. So there was an operation control center, and then the onboard and the wayside. So I'll explain a little bit more in the next slide. So there were various modes, driverless, which is the Goa 4, driverless attended, which was Goa 3, and then driver assist, you can say it was not Goa 2, but it was Goa 1. Both were Goa 1. So we had an existing ATP, which we did not want to remove because it was a business continuity for Rio Tinto. Rio Tinto is not a railway operating company. It's a mining company. They make money by selling iron ore. So we had to keep this. So we design in such a way that you can have both the ATP for some time and it can be taken out later. But the legacy was the L15,000 Swedish one, and enhanced was the ETCS one. And obviously it was passive, driver assist, driverless attended, and driverless. So this is the overall system architecture. We did not call it RBC because there was so much of apprehension at that time. And I remember I was leading that discussion to get ETCS into freight. Nobody wanted to touch it. They said RBC, ETCS is for high-speed train and passenger. Nobody wanted to touch it. So we called it VSS, Vital Safety Server, in line with PTC to sell it. And basically it is nothing but baseline 2230D plus freight function, national functions. So, and we had interlocking already available there on the line, across the line. And then obviously there was a Swedish ASK balises, whereas the ETCS Euro balises are FSK. So we could not remove the ASK balises. And we had an existing TMS from Ansaldo, and that had to be enhanced for driverless. Obviously, the train had to be given everything that you can think about, ATP, ATU, etc. That I will come later. So this was the architecture. It's the world's first where the RBC or the VSS is in Perth, 1,500 kilometers away from the line. And the communication between the operation control center, where the RBC was situated, and the TMS was through what you call a public line. Although dedicated with a 40 Mbps line for Rio Tinto, but they were carrying their own telephone and admin lines, etc. as well. So it was an open network. And then obviously the TCS or the TMS. So what we did was that we put a gateway, which was the nothing but the SIL4 platform that is used for RBC and interlocking. We had microlocks all along the line and some micro tracks, which Mr. Banerjee knows very well, which and no optic fiber on the mine side. So micro tracks communicate through the rail, interlocking to interlocking. So we had no optic fiber there, whereas in the section from the port to Rosella, we had optic fiber. So we put what is called a vital SIL4 system as a local gateway to collect the data from interlocking, and point-to-point radio to collect from the micro tracks through that which we call the wayside message server, and bring it to the gateway, which was was nothing but the same platform as RBC, and that was on the yard in the railway network. And then from there, it was brought back to the RBC at Perth, 1,500 kilometers away. And the onboard was obviously there, and it was not using GSMR. So this was an implementation where we use packet switch data, not circuit switch data. So it was using a 400 megahertz radio system. Okay. As you can see that this was the system infrastructure. So operation center here, the VSS, which is nothing but RBC for freight functions, TMS automation, and then you can see here with radio access and wherever we could do with fiber, where we had fibers, brought it to the gateway and brought it back here. That's very, very complex system. The onboard, and this is again, I don't think it exists anywhere. So apart from the packet switch data, which was going through that 400 megahertz radio, we also use the satellite communication for a backup, when the normal 400 megahertz between RBC and EVC was dropping out because of radio holes or failure, the data RBC and EVC was communicating through satellite. So as you can see, this was the existing ATP, what was running, the legacy one, the L15. So we brought all the equipment. So as you can see, we had the satellite and the data radio, which was the 400 megahertz, and the WiMAX. WiMAX was for data downloading, etc., and the locomotive control system. Then we put all the BTMs and we put the new EVC. So then we had to do a selection between enhanced or the legacy. And on top of that, we had that ATO. We put an ATO with a driving strategy engine, which is absolutely completely 180-degree different from what is normally in metro. This is a 2.5 kilometer, 32,000 ton train. So the train dynamics is completely different. So we use from New York Airbrake a driving strategy engine, which was integrated to become the brain of the ATO. And finally, we had the locomotive hardware interface, then a video image capture system, and this is what it looked like. So as you can see, EVC, legacy, selection there, ATO, image capture system, obviously the BTM, the odometer, the tachometer, and the WiMAX, satellite, and data radio. And you can select Go 1 to Go 4. So that's what the onboard looked like. Now, the important thing to understand is that this project was funded by Rio Tinto. So all the product development to make from high speed to this. So I was leading both the product development. I was in R&D department at that time as well. So I was leading all that effort with the team in France and Europe, Italy as well. So as you can see that these are the different modules within subset 26. The yellow ones are the ones which is part of subset 26, but we modified it and customized it for freight. The green ones were retained as it is. But the new ones, as you can see, we created the virtual bullies one, train integrity management, and we had electronic control pneumatic brakes, ECP. And then we had to create the ECP management as well. IP stack for Euro radio, so no longer circuit switched, but packet switched. And the driver interface was also adapted for freight application. The startup mission was not the same as we know in ETCS, adapted to freight. Mode management, a number of different modes came into play. And then the wayside air gap management, because we were using ASK balises, not FSK balises. So we were taking the ASK balises, translating it into the FSK format so that the EVC can understand the same language. And we actually modified the braking curve. So now in baseline 3, we have a little bit more harmonized braking curve. But in baseline 2, there was already an ERS spec. So we took that and created at least 2 different levels of curves. One for electronic service brake through the ECP, which was modulated 0 to 100%, and the electronic emergency brake 120. So in an ECP brake, you have RTUs on each pair of wagons. So when you send and there is a head end unit and a tail unit, and there is a train line and a cable running through the whole consist. So once a command is given, it applies at the same time on all the wagons. And that's why it is much more stable. And we adapted this in order to create this braking curve. Roy Hill was another one which is equivalent of class 1 PTC. It was again in the desert, 340 kilometers of greenfield railway. Now it is running. Here you can see exactly the same architecture, except the interlocking is now centralized. And the TMS is also included in the interlocking platform itself. So no more traffic control system. Exactly, except some train graph, etc., which was separate. Same onboard architecture, but no more balises. So we were using the GPS-based LDS, which is SIL4, which was trialed out in Sardinia. And then for Roy Hill, it was basically done for Roy Hill into a SIL4 positioning system. And obviously, as you can see, the object controllers on the way side. So all the interlocking function is centralized. So Tetra was used, not for voice communication, but for train to wayside communication for actual data transmission. So this was the system that was done for Roy Hill. So as you can see that we had the VSS, we continue to call it VSS because of the issue of acceptability. So it is nothing but RBC plus freight. And we had the wayside interface unit. And then we added this ATP, the display, and the ATO, which was optional. And another innovation that was done was that the people would recognize this as the ETCS DMI, the ERA DMI. and the bottom one is the PTC DMI, which we saw from WebTech. So we actually merged them together for the freight application. So we created a mixture of ERA plus the PTC DMI. So one can now see the MRSP here as well, like it is done in PTC, and the situational awareness with the track layout also, which is shown in PTC. But the rest of the information was still. And this is an example of hybrid, because in between the crossing loop, it was moving block. But in the station area or the crossing area, which we can call it a station, it was virtual block.
Vijay, will you be able to hand over to the
1 minute, the last slide.
Yes, thank you.
So this was another thing that we did with a handheld position management terminal. So this was basically communicating directly through Tetra to the RBC or the VSS. And this was at SIL2, being a ruggedized terminal, but not a safety architecture of the hardware. But we applied some techniques of 61508, kind of buffer reading and buffer cleaning and writing memories, and then having all those techniques of 61508 to make it into SIL2. And this is what was used to take possession from the wayside. So once it is taken the possession, the trains will not be allowed to enter. So you can say it is safe with this SIL2 HMI plus the dual, let's say, dual acknowledgement and confirmation from the operator. But I would still not call it a SIL4 equipment. It is a SIL4 function, but not a SIL4 equipment. That's it from me, sir.
Okay. Thank you, Vijay, for your excellent presentation and your very in-depth analysis of the modern system and the modern trains. And we are really very, very benefited from your vast experience, and you are really a train control man, as I can see, very, very nice. So, and now questions, anybody has any queries or any explanation you want from him? But excellent, Vijay.
Thank you, sir.
Okay.
I'm happy to answer.
I have a very,
Yep,
I have a very simple question for Vijay.
Yep,
Yeah, can I ask?
Yeah, please.
Yeah, very simple question. You see, according to me, there's a misconception that many people classify ETCS level 1 as CATC. So what is your view? Because knowing that ETCS level 1 will not have continuous authority. So would you still say it is a CATC?
Actually, Prashant, there are two things. In subset 26, it is defined as spot transmission, intermittent transmission. So when we talk about, so there are two aspects to this. One is the continuous or intermittent transmission. And the second is that is the what we call the supervision of the speed and distance. Is it continuous? And the third is, do we update it, this movement authority as we go? So from that point of view, ETCS level 1 is spot transmission with the balises, intermittent. And yes, it is a continuous supervision from the ATP. But as far as the update of the movement authority, etc., is concerned, it is not possible unless you come near the next balise or if you have a radio infill. This CATC definition, Prashant, if you remember, I and Prashant were together in Delhi Metro from 1998 to 2005. We did line 3 together, 3 lines. So Prashant, this CATC is actually a thing that should be dropped in my view. There is nothing called CATC. It is called ATC world over. So in any case, given the definition that you and I both know that happened in 98, it is not CATC. It is absolutely not CATC. It cannot be classified as CATC.
Okay, thank you, thank you.
One question. Then PTC, what is the accuracy of GPS? And here also ETCS level 3, your train control also you use GPS. So what is the resolution of GPS what you have deployed?
So, sir, there are two aspects to this, and I will be very, I'll be very cautious in answering this. So when you apply on a single line railway, single line track, okay, with some points and crossing. So obviously you have to look at for the lateral and the longitudinal accuracy.
Yes.
So I don't remember the exact figure, but the longitudinal was some meters. But the issue is not the longitudinal accuracy. The issue is the lateral one, because this is where you have to discriminate between parallel tracks.
Exactly.
So and for that reason, when we had a crossover, since it's a single, and we had reference LDS stations along the line as well, wherever we had a point and crossing, as well as an LDS on the train. So you can call it, it was kind of a DGPS. Okay, but the logic which we built into the RBC as well as on the onboard is that we utilized it in the sense that we took the point position as one of the inputs into the algorithm.
Okay.
So if the point is reversed,
similar strategy which was adopted in ACD deployment in NF Railway. Of course, ACD has been discontinued now. I don't know whether you have read about ACD deployment on Indian Railways.
I have a little bit, sir, but I can tell you that this LDS, which we did for Roy Hill, so long back, it is definitely SIL 4. It has been assessed by the ISA's ETL certified.
In India, this ACD was not assessed for any of the SIL levels. It was treated as a SIL 0 system only.
But then in that case, sir, as I said, the RBC was having a module inside, which was taking into account the offsets and that it was calculating based on the reference stations of the LDS. And as well as then in the logic, there was the what you call this point position that was taken into account as well. So when we talk into the product life cycle, these are taken into account at various levels. So operationally, for a single line, it was suitable. From a process point of view and the platform point of view, it was SIL 4. But if you want to apply it on Indian Railways, I think it's going to be a big mistake.
No, in fact, TCAS, which is being developed in Indian Railways, that is again based on GPS only.
But GPS can never be more than SIL 0, sir. GPS has no integrity because unless you use a military level accuracy that the US government will never give us.
We don't know the future of TCAS or even the present status. We are not really aware. I think somebody from working person in the railway board could apprise. If
I was involved in this definition of this Roy Hill system. I was, as I said, I was in R&D for many years. Mr. Banerjee knows, for 6-7 years in Ansaldo, working for the headquarters. I think LDS was developed as SIL 4 platform, but I do not think it can be applied on parallel tracks.
Okay.
It has no integrity more than SIL 0 or no SIL. So very difficult.
So shall I start sharing my presentation, Somnath?
Yes, please.
Yes, please. But your video is not coming.
See, actually, there was some problem I was facing with the network, so that is why I had switched off the video. I'll just try to switch it on again. Now, now is it coming? See, video is getting freeze. I don't know.
Now it is come. Thank you. That is much better because yeah.
Okay, so I'll take control and switch on the presentation now.
Yes, please. Thank you.
Tuteja, your video is frozen.
There's some issue. I'm just trying to share the presentation first.
Okay.
So there's some network issue which I'm facing today. I don't know. It's a broadband connection, but still.
If you are having a problem with the presentation being projected, you can quickly upload it to that same place where I have given you.
Just
and I can.
I'll just try to share it.
Come on. How are you? While Tuteja is managing his presentation.
How are you? Thank you so much. Good evening.
Good evening. Thank you for joining.
Good afternoon, Mr. Balram. Good afternoon.
Yes, you will probably have to hear a very interesting discourse Vijay had given in the recorded version. Yeah. But anyway, the recorded version has a many viewers, almost 400 at least. So
yeah, I was just listening that TCAS is using GPS. I would like to clarify here that TCAS is not using GPS for the purpose of location or location determination. It is only for the purpose of synchronization of the entire system. It is not used for location determination.
So location determination is by still by track circuits or axle counters?
Yes, yes, it is by track circuits and the interlocking interface is there.
Okay, then in that case, there should not be an issue because if you're only synchronizing the rest of the system with GPS, should be okay.
Yeah.
If I remember correctly, the TCAS wants to for the midsection collision, they were supposed to use the localization by GPS.
And they are not doing it now.
They have changed the total philosophy, then it means.
In fact, there is a station TCAS interface which radiates its status, and there is also this RFIDs along the track, which keep on correcting along with the onboard odometer, keep on correcting your location all the time. Every kilometer there's an RFID tag which has to be sensed, and even if it is missed once, I think you can always correct your location.
This is concept of not a concept that the use of more accurate satellites, the GNSS, I believe they call it, for the more accurate determination of positions. So that is not used for any of our ETCS.
No, sorry, it is not used because as I was talking about Roy Hill, we are using the normal GPS, but you need to have a DGPS equivalent capability. So as I said, we created this module in the RBC, as well as we had reference stations of the LDS on the west side, wherever there was points and crossings, and on the train. So it works on a concept which is, we were not using any RFIDs at all, zero. There was no RFID. So it is similar to a class 1 PTC. So as I said, it is very difficult to use it for a double line track or a triple line section. You can use it for a single line, which is what we used in Roy Hill. So on a single line with one crossover somewhere, one siding, you can use the point position. That's what we used, a point position in the algorithm. But you can't use it for a double line section or a triple line section. So, and GPS has no integrity, absolutely no integrity. I can assure you that I have studied it in great detail during the development days. GPS will not provide you any integrity unless it is a military level one. What the Europeans are doing, that may bring some difference. But right now, I don't think it's the case.
Tuteja, are you ready now?
I'm just trying. I don't know.
Somehow can you upload it? Because what I can do is, if you can quickly, can you upload it?
I sent it to you on the WhatsApp. See if you received it.
WhatsApp also you can send.
I sent it to.
No, yeah, just a minute because I'm on my computer. WhatsApp. Okay. Yeah. Okay.
Because I'm trying to share it, but somehow it is not happening. There's some problem with either my PC or.
Yeah, no, that's fine. Don't worry. You, yeah. I think have you sent it already?
Yes, I sent it.
Yeah, I can see that. Yeah. Okay. Give me a second. I'll just download it and then present it.
Okay.
Not a problem. This is
the first time that I'm facing this problem.
Now it happens. You know, networks, technology.
I'll just log off and log on again. I'll just leave and rejoin.
Okay, you can. But in the meantime, I'll start presenting your thing while you come back. Yeah. Okay, I'll present your. Where is the content from? What do I? Oh, I will. Windows. Let me open this. I've just downloaded it.
Good afternoon, Arun.
Good afternoon, Ratan. How are you? How are you? Long time.
Yeah.
Back from US?
Yeah, about 3 weeks ago.
Okay.
Slideshow. Okay. So I'm just getting today's screen. Okay, I'll upload it on the. Just a minute. Sorry. Like Chrome gone. Yeah. Okay. Yes, Windows. There you go. Can you see?
Yes, now
Yes.
yes, can see it now.
Okay. So
Okay.
I'll just go to where is the mode? Yeah. You let me know.
Yes.
Yeah.
Okay. Thank you.
So
Thank you so
you can
much.
hear me, right?
Yes, I can hear you. I hope my voice is also
Okay.
audible.
So I'll go.
Hello.
Yes, I can
Yes,
hear
yes,
you.
Okay.
Everybody
So
else?
everything is fine.
good afternoon and good evening, everybody in different geographies. So it is really a pleasure to be present in this group and talk about my experience of signaling and rolling stock integration. I have been recently, last 4 years, I have been working with Louis Berger and working as a part of general consultants for Mumbai Metro Line 3, which is a fully underground line, right from Kolhapur to Sri, which is about 33 kilometers. And this line, the signaling which is proposed is CBTC with the ultimate aim to have a UTO operation. Actually, we are aiming from the day one, but let us see how we are able to achieve it. So next slide, please. So as we know the background, we are all signal engineers. So conventional signaling and train control systems, they rely exclusively on track circuits to detect the presence of trains. Information on the status of the track is provided to train operators either through wayside signals or train-borne cab signals. Now, the location of trains can only be determined to the resolution of the track circuits. If any part of the track circuit is occupied by the train or by the block sections, block instruments as we used to use in the Indian Railways. Just keep it in this slideshow mode, Somna.
Yeah. Just sorry, I just clicked the wrong button. Yeah, you're in the second slide.
Yeah. So the information that can be provided to the train is limited to a small number of wayside signals, signal aspects, or a small number of speed codes, which can be done with the cab signaling, which we used to do it through track circuits, coded track circuits, or through Bellis-based systems. For a wayside signal, automatic train stops, but without continuous cab signaling, enforcement is intermittent. So what we used to work was always on an intermittent control systems. Next slide, please. So communication-based train control is the dominant technology for automatic train control for metros today, as Vijay had already given background of CBTC systems. So in fact, CBTC, as what we are seeing today, based on the Wi-Fi and WiMAX communication, is not the first CBTC communication. Earlier, the communication-based train control systems deployed inductive loops. And in fact, the first, there was a train in '87, which was inaugurated, Darlington Light Railway, which worked on this system and is still operational today, which was a totally driverless system in the London. Now, the basic characteristic of CBTC system as includes determination of train location to a very high degree of precision, independent of track circuits, geographically continuous train to wayside and wayside to train data communication network to permit transfer of significantly more control and status information. Today, we all know that when we want to run a UTO-based trains, then we have to transmit a large number of informations from train to ground. So naturally, we need a very wideband network, so which is now facilitated by by a radio network which may be 100 Mbps or 500 Mbps and a gigabit Ethernet backbones. Next, please. So under conventional system, we all know that interface between the signaling and the rolling stock was always manual. The signal driver had to see the signals, recognize them, and respond to them. And driver was always expected to respond to the signal. If it is a red signal, he was supposed to stop short of the signal. If it was yellow, then he was to reduce the speed to a predetermined levels defined by the rules up to the next signals, which allowed him to go up to the next signal, which was red aspect, and green indicated that he can go through. Now, errors in the response led to accidents, sometimes resulting in number of fatalities. On Indian Railways, we are all very well aware that number of SPAD cases are galore, and number of SPAD cases which used to result in collisions have also been quite a few, and which have resulted in number of casualties as well. So there was a need to automate response of the rolling stock in case of error by driver. So which led to the evolution of automatic train control systems, and which led to installation of onboard train control communication systems to help them communicate with the wayside signals, which was done by means of balises and connecting them to the signal aspects, as we have done in ETCS level 1 or in the auxiliary warning system, which we implemented way back in 1988 in Western Railway suburban and Central Railway suburban sections. Next. So in a CBTC project, the rolling stock interface is the most important and critical. Now, the typical composition of the signaling and rolling stock subsystems are given in the table below. Signal system would constitute carbon controller subsystems, data communication subsystem, a video transmission system, and a train wake-up unit. And rolling stock would consist of train assembly, its train characteristics, and train control management system and its electrical lines. Next. So here it is represented as how the interface is driven by the rolling stock functional systems. Actually, SIG RS interface is primarily focused and driven by the RS functional specifications, which lead basically the interchange of signals between the carbon controller and the train TCMS train control management systems. And then there's the DCS RS interface, which is basically for the data communication system that is to the installation in the rolling stock and communication with the. Basically, DCS does not communicate with the rolling stock directly. DCS communication system is connected to our carbon controller, and from there it communicates with the various RS subsystems. Basically, the train control management system is the control center of the control center of the train. And train wake-up unit is a special unit which is used to wake up the train from sleep position in a UTO mode. Next, please. So this is representing again the various interfaces as so CC to TCMS. There are mechanical interfaces for installation. There is a power supply interface, and there are electrical interfaces for data interchange. And these are the interfaces which, and similarly DCS interfaces with the again mechanical interface for installation of antennas, installation of the radios, and then power interface for the taking the power source from the rolling stock, and the electrical interfaces. Then TW again interface, there mechanical, electrical, and power interfaces are there. And these interfaces are various train assembly, train control management systems, and train characteristics are which are integral part of the system, which are needed to be programmed into the system so as to enable the carbon controller to effectively control the train services. Next. So these are defined again in a tabular form that mechanical interfaces are basically support cabinet, cubicles, brackets, nut, bolts, screws, etc. Then power interface is basically power consumption, power distribution with circuit breakers, power supply connectors, and wires, etc. Then electrical data interfaces from train wake-up unit to rolling stock, and rolling stock to train wake-up unit, carbon controller to the rolling stock, and rolling stock to the carbon controller unit. Various diagrams are required to be prepared with wires, cables, connectors, relays, adapters, CC network with cables, etc. There's a complex network on board in a metro system, which is used. And it's a redundant network which is used to interconnect various devices and various subsystems on board the train, as well as interface with the signaling system. Next. So basically the carbon controller, which is the main heart of the system, is basically hosts the functionalities of automatic train operation, which is a vital application, and automatic train operation function, which is a non-vital function. The core of the CBC carbon controller consists of a safety carbon controller computer, which hosts the main part of the ATP application, which is SIL4, and then optionally ATO application, which is not SIL, which is SIL0, which may be then processor boards, which are 2 out of 3 systems, or maybe depending on the design of the manufacturer, it may vary. And then vital IO cards, power supply boards, event logging, etc. Next. So basically, carbon controller, the main functions are handling of the train wake-up and sleep procedures required in driverless operation, handling of the train initialization and self-checks, train motion and protection during the train's motion, monitor the train speeds, energy and spacing, location of the train by means of beacons and odometer, update the dynamic track description, end of authority variants, point status, signal status, etc. Precision stop of the trains in station management, station stop and departure time management. All these functions are regulated and controlled by the carbon controller. Next. Then other functions which include traffic regulation, process movement authority limit, apply the TSR and work zone coming from LC. The LC is the line controller unit, which is a special equipment which is provided by the Alstom systems. In other systems, it may be for this function may be carried out by the zone controller itself. The automatic operation of trains according to both safety rules, speed limits and points to protect, regulation constraints, and assistance to driver during non-driverless operation via dedicated driver HMI, and handling and generation of alarms to ATS and maintenance support systems. Next. So when we talk of CC to train control management system, the train control management system is equipped for control, protection, fault diagnostic, display, record, and data acquisition of the train. It is a complete integrated system for control and monitoring of functions, performance parameters of the train, its systems and subsystems. TCMS is generally SIL 2 compliant. The network communication technology, which is used on board train, basically uses based on Ethernet, and other subsystems are also using the Ethernet connectivity on board the train. Next. So this basically shows the CC to TCMS network architecture. So there is a core CC Ethernet network. There are two core switches and which are connected to the TCMS network, which is again a redundant network. And there are the main processor unit, which is there is a master and there is a standby. And the carbon controller also is installed in both the cabs, which each act as a standby to the other. Next. So TCMS is connected to the redundant carbon controller network through gateways, and gateways are connected to two CC networks. TCMS subsystem network interface is based on standards technology and protocol. It basically uses the IP technology. In addition, there may be a number of direct hardwired IOs within the carbon controller and the TCMS, which are used for some safety outputs and safety inputs. Next. The role of DCS is basically to manage the data communication between the signaling devices of the CBTC system and VTS devices of VTS system. VTS is actually video transmission system, which is installed on board the trains to transmit the live video streaming of the saloon surveillance system to the OCC, which is the essential requirement in case of we want to operate a driverless train or a UTO train. So DCS subsystem provides basically end-to-end communication for automatic train control systems, and also it communicates to the automatic train supervision system, which is basically the overall controlling system for the operations. Next. It also interfaces with the communication computer-based interlocking, which are installed at the stations, which can be a distributed interlocking and can be a centralized interlocking as well. So in most of the systems nowadays, the concept is to go for a centralized interlocking, but maybe one or two interlockings may be provided depending on the operator's choice. And object controllers are installed at other wayside stations because the number of crossovers provided are quite limited in the metro environment, unlike railways, where in suburban section we practically every station had crossovers. Where in a 33-kilometer line, we have planned to have only crossovers at 5 stations. And the DCS subsystem, just go back to the previous slide, please. So DCS subsystem, as we have discussed, the protocol used for DCS wireless system is basically IEEE 802.11 standard, and radio system is generally implemented in the ISM band. But this is implementing the radio system in the ISM band has its own issues it can arise. Like Kochi Metro had faced the problem of interference when they were operating their CBTC radio system in 2.4 gigahertz bandwidth. So, but then they had to change to 5 gigahertz bandwidth. So we have to be careful. And actually, I hope that in India, like a specific band is being allocated for the railway operations. So I hope that will allow the operation of CBTC systems in that band also. Next. So this is the typical DCS architecture. So the data communication system constitutes a radio system as well as a backbone, optical fiber backbone. For the convenience sake, we are provided we are calling these networks as red, blue, and green network. So red, blue are basically the CBTC networks, which are redundant CBTC networks, both working on independent fiber backbones and taking the data to the OCC. And green network is exclusively used for only VTS, which is 100 megabit, 100 gig 10 gig network and CBTC network is a 1 gig network. So it's both working in the rings so as to provide a high level of redundancy and availability. Next. So the DCS CBTC radio modem is placed in the both the cabs and it is connected to the ATC onboard LAN, and DC-DC converter is provided along with the DCS CBTC radio modem to power up from the onboard power supply. And there are one pair of CBTC antennas are provided, and the location of the antennas may be dependent on the choice whether inside or outside both ways the antennas can be provided. Next. Now, video transmission system caters for the bidirectional data/video transmission from train to operations control system. Onboard cameras, onboard network video recorders are generally provided by the RS. And again, the technology used to stream onboard CCTV video is based on IEEE 802.11 standard only. And next. So this is a typical onboard VTS architecture. So we see there's a network video recorder and the salon cameras are connected to the network video recorder, and the network video recorder can store the images for store the footage for 15 days, and the cameras itself, for which we are catering in our system, can store for 48 hours the images, and these cameras are addressable, and from the our video management system, which is we are installing by the SND for the analysis of videos, can address each and every camera individually and capture the footage and retrieve the footage for analysis. Next. So the scope of the work of the rolling stock is to provide onboard network cameras, configuration of CCTV cameras, IP addressing plan for onboard network devices, CCTV live images from onboard cameras as per display system requirement is sent by rolling stock network to DCS on a suitable port for carrying to the track side. DCS system interface with the rolling stock network to receive CCTV live image and uses onboard rolling stock network for communication among different DCS devices. And for handshaking purpose, master slave identification of redundant DCS devices. Next. So the train characteristics is important parameters which are basically each project dependent, and they constitute train dimensions, weight, wheel characteristics, position and characteristic of the train, motoring and braking characteristics. These are essentially required for providing efficient and effective control by the CC and the TCMS, because then only the braking curves, etc., suitable braking curves can be applied, and suitable motoring demands and acceleration and deceleration commands can be given to the rolling stock by the carbon controller. Next. So the technical reaction times of this also defines further parameters like technical reaction times of the rolling stock equipment, parameters related to emergency brake, motoring and braking delay, response times, train door delay, behavior for automatic driving, car characteristics for the gravity center of train for the train computation. So all these things are required for proper train control to be done by automatically. Next. Train wake up unit is used to provide capability to trigger train wake up in response to a command coming from the OCC. TW is connected to DCS and CC modem in order to receive wake up order from OCC and to report train wake up status. TW basically is connected to the train wake up line, and it initiates various subsystems of the train and starts the process of carbon controller also power on, and it is then combined tests, etc., are carried out on the train. Next. Now these integration tests, why do we conduct a lot of integration tests? These tests will enable to simulate the CC equipment in a dynamic mode to supervise all the actions ordered by the ATC. The aim is to check the CC equipment inside the RS are working properly in the real-time operating condition. The train with CBTC equipment under test on board circulates on the train test track to validate the proper operation of these equipment. CBTC ground equipment like ATC, ATS, JETC, LC are simulated by means of using a network links and a simulator. So pre-established simulation scenarios are created using simulators existing functions, which are used to test the ground related functions in front of the onboard equipment to be tested. Next. So the typical test what we perform on the during the process of integration test are various functional tests, which include train to wayside communication, track side, partially or fully commissioned, driving train in all modes like restricted mode, run on site mode, then train location memorization, train wake up test, track side transmission, free propagation antenna testing. Next. Then driving train in the ATP mode. So we have to see that the train does not perform emergency braking without any reason. The end of authorities interpretation, ensuring that they receive it and they are correct. Target speed displays, emergency brake triggered when overspeed, driving mode in ATO and ATP, ATO and UTO modes. Next. Odometer testing, beacon testing. So all these tests are typical tests which are required to be carried out. And this what it ensures is that when we get the train from the test track to the main line, it basically is received with a high level of maturity. And also it is important to note that on the test track, basically we carry out the tests only at low speed up to 25 km because the test track lengths are generally limited to about 800 or 1 kilometer maximum. So the Alstom factory has a test track which is about 800 meters. In depot also, when we construct the test track due to the limitations of the land availability, generally the test track lengths are quite limited. So high-speed train tests which are required to be carried out. They are carried out on the main line, which perform all the tests which are required. Integration of all the equipments like signaling, platform screen doors, and other interfaces with the other subsystems like power SCADA, and there are number of other interfaces like tunnel ventilation, all such interfaces are to be tested during that period. And the harmonization of doors, that is another important test when we have to do with the UTO, harmonization of PSD doors with the rolling stock doors. So that is critical operation of critical tests we need to confirm before we really declare that train is fit to fit and ready for operations. Next. So this brings an end to my presentation. Sorry that I couldn't do it myself. So sorry to trouble you, Somnath, because
No, it's all good. No problem. This is a bind. Thank you. Don't worry. That's fine.
So thank you, Tuteja, for your very interesting lecture, and especially the people who are working with this train interface, they'll be greatly benefited from this. Any questions? So if there is no question, I would request Somnath Banerjee to summarize and then conclude this session.
Thank you, Ratan, for anchoring this interesting discourse tonight. Tonight in Australia, that is. Today in general, yeah. And thank you, Vijay and Tuteja, for sharing your experiences and your knowledge with us here today. There has been the physical presence has not been very large at this time. Probably, I think Saturday. I find that Sundays are probably better now. Next time we'll have to discuss this. Why the physical presence was much less, but this will. I know that when it goes on the YouTube and because I provide the links on the various social media. There are a lot of visitors to it, so we had conducted them in a very interesting way. Thank you all for that. And I can close this meeting. If anybody else has something to say, please let me know. Otherwise, I can close it.
So yeah, at the end I want to thank everybody, and especially Vijay. I've seen after a very, very long time. You know?
It's a pleasure, sir. I'm seeing you after you left Google, sir.
And Tuteja, of course, I have seen in between quite a few times. But it's very interesting evening.
Virtually only.
Yeah.
And
So,
for me also, sir, to see Prashant Rao in the same forum, because me and Prashant Rao were the first two people who did the first 3 lines of Delhi Metro together. Then I left. Prashant also did the. We worked together for 7 years, I think.
Vijay.
Yeah. Yes, sir.
When we were talking about the same manufacturer of signaling and rolling stock, I can vouch from my experience that we had enough trouble with Alstom rolling stock as well as Alstom signaling to have a final proper integration.
Sir, I have had experience with this as well. So there are two issues here. Basically, what happens is that when you're talking about train characteristics, etc. So there are a couple of points that we should always keep in point. One is that when we talk of the different timings, it's not only about the typical braking curve characteristics like the traction cutoff time, etc., and the brake delays, etc. The real important thing is to look at for PSD, and that is where we need to find the Alstom in this case for signaling and train is to look at when the train is immobilized from the time it detects the zero speed to the time it sends the door open command. That's where the trick is. I can share you my knowledge on this is that this is where the trick is that they eat at least a few seconds per platform. So it will have a big impact on your journey time.
See, we have a 30-second dwell time, out of which roughly closing and opening time is taking away roughly about 6 to 7 seconds.
That's why I'm telling you, sir. It is this is where Alstom plays with it.
So we had a lot of problem in synchronizing and harmonizing this PSD opening and closing along with the rolling stock doors. So that was the most, and we had to bring. There was another dimension, another stakeholder, that is at Fangda, which is a subcontractor for PSD by Alstom. Although PSD is also by Alstom only, but they have engaged Fangda to provide the PSDs.
So this is a problem in Singapore. This is a problem in Hong Kong. This is a problem every project that I know of this PSD door synchronization. That is why everybody is specifying these days. If you look at the Zhurong line bid that was won by Siemens recently, and you look at the newer bids which are coming out, obviously I can't talk about the work that I'm doing right now because I don't have permission to talk about it from my organization. We have specified these things in greater details. So we need to look at the sequence diagram of all this and the sequence of timings. And if we don't do that, then it is a problem.
We did all that exercise. Despite that, we were not able to. We were able to achieve only this much, so, but we had to had so many meetings with the Fangda, Alstom together, and like that we had to resolve, come to.
This is always a problem. This is always a problem. That's why specification is very important.
Yes.
Vijay, I would like to say one thing regarding what Mr. Tuteja said. You see, the basic problem in India, what is happening is the way the tenders are being done. The easiest and the most convenient way is to combine signaling, telecom, rolling stock, everything.
Yeah.
The client, that is the easiest way for a client to do. But I would say that is the biggest mistake. The moment you have a common OEM for signaling and rolling stock, you never know what they are going to slip in. The client will never come to know of many things. And the basic thing is, in the current market, if somebody is combining rolling stock with signaling, then finally you are limiting to only 3 bidders. That is a major problem.
Prashant, if you remember, Metro Line 1, DMRC Line 1, Line 2, and Line 3, it was Rotem and Alstom, Rotem and Siemens. And how many fights we used to have have all these interfaces sorted out.
So this is what I'm saying.
I totally agree with you. That
in Mumbai Metro Line 3, there was a separate tender for rolling stock and separate tender for signaling and telecommunication, but still both landed in Alstom's lap.
That is, you see, that finally what will happen is, you see, this is a mistake which was done. That what incidentally happened in Kochi also, and at a very late stage, many defects were discovered.
Lucknow is also same.
But Lucknow is also same. That is why I'm saying. Finally, at a very late stage, they will discover many issues because nobody is going to spend energy at the initial stage. So that becomes a mistake.
Prashant, you are right. And I think, as I said, I'm not talking the details about that. But we also faced similar problems in the recent past. So the specifications that we have issued now has gone to the level of details which an OEM level knowledge is required. Because in order to get this things on the table between the two bidders, because even if you look at big suppliers, including Siemens, Alstom, and Hitachi, I've worked with all of them. They are two different business units. They may be same company, but they're two different business units with different direction and different motivation. So I don't think that giving it to the same supplier necessarily means better integration. I think the trick is, that's my personal opinion, The trick is specifying it properly
Yes.
to the level of detail
that is
that
the
is
key.
required.
Key is a proper
Yeah, that is the key.
specifications.
So, can I speak?
Sure.
Yeah, before I think you conclude the session, I would like to request all of you to please take note of an international conference which we are organizing in India. And the sponsor, the coordination done by IRC London, and we in IRC India, along with the support from the Ministry of Railways, are trying to organize this conference on the 24th and 25th of February 2022. The conference theme is basically the intelligent railways, which we all are talking about. And I would request all of you, in fact, you have any papers to submit for this conference, you are welcome. And that will be a useful forum where we can share these ideas. Incidentally, I'll be part of the technical committee on papers with IRC London. So we can push through these papers. We have requested IRSC to allow at least 12 papers to India and balance 4 or 5, maybe 6 papers to UK and Australia. So I will request the forum here. If they have got papers, they can share with me. We can forward it to the IRC technical committee, and then we can focus on the subject. Apart from this, I think you are working on big organizations. You should also be able to sponsor or maybe showcase your products or your systems in this conference, which also has a small exhibition portion of it also. That's what I wanted to mention. If especially people who are working with companies, they can always support the conference. I think there will be papers on, there will be 6 different sessions. Number 1 is about the train control systems, which includes radio-based systems like CBTC, ETCS, TCAS and all. There is a session on operations control centers, TMS and CTC. There's a session on predictive maintenance, condition monitoring and predictive maintenance. There's a session on digital networks and data networks for the purpose of digital transformation of systems. And there's a session on tools for application development and for the purpose of testing, VNV and project management. So these are the possible sessions. I think in any of these areas, if you feel like submitting papers, you are welcome. Thank you.
Thank you, sir. But unfortunately, we can't come to India at that time.
No, we have kept a digital interface also. We will have the recorded version of the paper, and only the Q&A session you will have to be online. That we have discussed with the IRC also. In fact, depending on the situation at that time of the COVID, it is possible that many of the people from IRC London also may not be able to come.
Yeah,
So,
they recently conducted, the IRC conducted one in London, the high performance railways one. Everything was online.
Yeah, that's true. That's true. But in India, I think this is in physical form along with the exhibition in physical form. So at least the people from the metros, PSUs, the Indian Railways, and high speed and NCRTC, they will definitely be participating. Maybe the participation from outside India would be minimal because I think we were expecting about 120. Now it will be going down to 40 or 50. That depends on the COVID protocol at that point of time, how much time you have to spend in quarantine. But definitely papers are acceptable. In fact, papers can also be published into the book which will be brought out on the occasion. Incidentally, our minister is also from the same field of electronics and communication, so he is too keen to participate in this particular seminar.
Good.
Thank you.
Okay.
Okay. So if there is nothing more to speak in this session, then I can close this meeting for the day.
Sure. Okay.
Thank you, sir. Thank you, everyone.
The others and for participating and contributing as well. Thank you very much. Have a nice day.
Thank
you all.
Evening,
Thanks,
and
everybody.
Thank
Thanks
you.
all.
Good evening to everybody. Bye.